Alright guys, welcome back. So today we're taking a look at 11.3 geometric sequences and series. So very similar to the previous topic, which was arithmetic, and these sequences are based on terms adding or subtracting by the same number. Geometric, the same idea, but it's now multiplying by the same number. And we call this number the common ratio. And we find it quite simply by doing the second term divided by whatever the first term is. Now, because we're creating a fraction, if the fraction is greater than 1, you'll find that this sequence is increasing in value, whereas if it's a fraction less than 1, you'll find it's decreasing in value. If the R value is negative, then obviously it's going to oscillate back and forth between positives and negatives, and so apply that same kind of idea. Bigger than, I guess, smaller than -1, it'll be getting larger, technically, because it's a so pretty much we're looking at the absolute value of 1 in reality for this, which is going to actually come very importantly. We talk about the idea of finding the sum of a series for this stuff. We'll get into that to the end. So the explicit formula we'll use to predict future values and everything, an is a1, so the first term, times r raised to the n minus 1 power. Very important to make sure the exponent is n minus 1, not just simply n. Also very important to make sure your r value is in parentheses. Not as vital if the r value is a positive value, because positive numbers for any power is the whatever, it doesn't matter. But a negative number raised to a power has to be in parentheses, so it's properly evaluated when you solve out the problem in your calculator. So here we go, we got our sequence. We need to identify our first term. Well, a1 is just simply the -6. And then our value of r is the second term divided by the first term, which is going to give us a -2. So we write our explicit formula. An is a1 times r to the n minus 1 power. And there's our explicit formula. They want us to predict the value of an, the ninth term. So we go ahead and plug in 9 for n into our equation. And then 9 minus 1 is 8. So you would just do -6 times -2 to the 8th power, where again, it's in the appropriate parentheses. And you'll find your answer is -1,536. So that's all we're doing. If they give you a couple terms to write your formula, they need at least the first term and the second term, so we can identify a1 in the common ratio, and then we can then go from there to find whatever other term we want in the future. Now, we don't necessarily have to be given the first term to be able to write our equation. We can kind of work backwards to find our first term. So we know that a5 is 1875 and r is 5. Find a3. So we need to find the explicit formula first, which means we need to get a1. So we work kind of backwards from the explicit formula. We know that a5 would equal a1 times r to the n minus 1 power. Well, a5 implies that's the fifth term. So 5 minus 1 is 4, so this will be raised to the fourth power. So that gives us 1875 equals a1 times 625, which when we divide over the 625, a1 is going to be 3. Which means our explicit formula, an, is just simply 3 times 5 to the n minus 1 power. So if we want to find a3, we're now plugging in 3 for n, so it's 3 times 5 squared, which will give us 75. So that's all we're doing. If we kind of have to work backwards. And obviously, in this case, there's not very many terms. We could have just simply divided by 5 a couple times there. Because if a5 is 1875, divide by 5, that's a4. Divide by 5 again, that's a3. Divide by 5 and divide by 5. There's nothing wrong with that, technically. But again, kind of like with the arithmetic sequences, they could give us absurd numbers, like a17 is this. Find a29 kind of thing. We don't necessarily want to keep on multiplying and dividing and just kind of accidentally make a mistake with that. Now, because we're multiplying, these things are exponential. So the growth is exponential, and they can get pretty large very quickly. They're probably not going to give us very large values of n to work with, but something to just be comfortable with the process of writing the equation. That's all I'm trying to say. We don't find some terms that's missing in the middle, so we do the same kind of thing we did for the arithmetic sequences. We kind of write it out. And we recognize that we are going to increase by r 1, 2, 3, 4 times. So it's not 3r's, it's 4r's we're dealing with. So we take our last number and divide by our first number. Gives us 625. And that has to equal r to the 4th power. So we take our 4th root of the 625, which is going to be 5. And technically, it's going to be plus or minus 5. Because we did an even root solving an equation. So there's two different answers we can get from this. If r is a positive 5, it would be 2, 10, 50, 250, 1250. If r was negative 5, it would be 2, negative 10, 50, negative 250, positive 1250. You can see in both cases we start at the same number and end with the same number. There's just some differences in the middle. In general, the answer key for most questions involving something like this would just assume r is positive because the first and last numbers are both positive. So that's generally how they kind of associate it. Whereas even if they were both negatives, they would assume r is positive. So pretty much if it's the same first and last, they're going to assume r is positive. If they were opposites, then they'll go with r as a negative. But they're not technically wrong if you wrote this bottom sequence here because it would still create the same scenario. Now, like with the arithmetic series, we have a geometric series sum formulas. There's two of them based on what they give us. So you have to always be given the first term and the common ratio. And the question is whether you're given how many terms there are or whatever the last term happens to be. So those are your two different series that do that. And obviously, for these questions, they could be something where we have to kind of work backwards to find A1, or we have to find R, or something going on there. We could certainly have that scenario. These will just be straightforward. Here's just give the information to find the correct series, but you could have to apply stuff we did examples in 1 and 2 or 3 to kind of find other pieces of information. All right, so here they give us the first term, the last term, and r is negative 6. So we're using that bottom of the two formulas there. So our sum, Sn, is going to be our first term minus our last term times our value of r, all over 1 minus our value of r. So in the numerator there, you got to make sure you're careful. You want to use your calculator, really. You can just do this in one step, probably your best bet. So just going to do the numerator, 1 minus this times negative 6. It'll do it correctly for you PEMDAS-wise because it's going to multiply the 46,656 by the negative 6, and the result do with the 1. And then 1 minus the negative 6 at the bottom is a 7. Either way, you should be getting 39,991 is what the sum should work out to be. If you don't get that, again, break it down step by step. Be careful how you're typing into your calculator, really. All right, so if they give us the value of n rather than the last term there, well, this tells us we want to find essentially S8. We have a little more information about what partial sum we're finding. So we'll call it S8 rather than Sn. So that's our A1, and then parentheses 1 minus r to the nth power over 1 minus r. So definitely need to make sure you're being a little more careful here. When you're typing in this, it's 3, and then again, your parentheses, 1 minus, parentheses on the negative 2 is essential, otherwise it's going to totally mess up the problem. It's the 8th power. In the bottom, you have 1 minus the negative 2. So if you want to write the bottom as plus 2, and therefore 3, which is therefore in this case cancels with the top. Awesome. Make your life a little bit easier. So just 1 minus the negative 2 to the 8th power, which is going to give us a negative 255. Or you could have done it all in one step from the beginning, especially if you have your newer 84s, the alpha y equals, which I've shown you multiple times on the calculator page how to use, is be very useful for that stuff. Now, we do have an infinite geometric series situation. This is where we can find the sum of an infinite geometric series, but this only works if the absolute value of the common ratio is less than 1. This is always kind of rambling about in the very beginning, talking about increasing or decreasing kind of thing. This needs to be less than 1, the absolute value of it. So if r is like a positive 1/2, that's fine. R is like a negative 2/3, that's fine. But like if r is a negative 3, no good. It cannot be. If the absolute value of r is greater than 1 in any way, then the sum will not exist. And if it's just equal to 1, there's not really... it also wouldn't exist, I guess, then either, because then the common ratio is 1, they're multiplied by 1, it stays the same number the whole way, so it's like 2, 2, 2, 2, 2, 2 the whole way. The infinite sum of 2's would be infinity, so it would not exist either. All right, so our formula is very straightforward. It's just a1 over 1 minus r. Now notice, if you forget to check the value of common ratio, will it work or not, you'll get a number here. So it's not like there's any way that it gives you an error message unless r is actually 1. Then it'll be a straight in your face error message there. So be very careful. Make sure you're always checking that r is, nope, too large or too small, whatever it is. So in this case, this one that does work, r is a half. So we're okay. So our infinite sum would just be 80 over 1 minus a half. It's just 80 over half, which is 160. So again, all it's going to look like in terms of, it being an error kind of thing would be if they gave us a1 is 120, let's say, and let's say r is a negative 3. That is no sum. It's not possible. Don't write infinite sum. That's not exactly what we're talking about here. We want to make sure it's diverging, essentially. So we don't, instead of converging, it's diverging. We want to say there's no sum to it. Now, theoretically, they might try and disguise that a little bit better. So rather than giving you as a1 and then r like that, they might give you the sequence itself. They might tell you, okay, so we've got a 2, then we've got a 4. Let's not do a 4. Let's do a 6, and then an 18, and then multiplied by 3 is 54, and so on there. So you're recognizing a1 is 2, r is 3, and again, no sum in that scenario. And so make sure you're very, very careful with that. Whether they explicitly tell you r value, you have to find yourself. The moment it is the absolute value of it is greater than 1 or equal to 1, really, you cannot do this, and there is no sum. Now, if they give us the infinite sum and tell us the first term, we can work backwards to find what the value of r was to create that. So working with our formula, that means negative 42. Sorry, pen died there for a second. For some strange reason, it turned off despite literally being just used. Love technology. So negative 42 equals a1 over 1 minus r. So we're going to go ahead and essentially put the negative 42 over 1 to cross multiply. Get negative 42 plus 42r equals negative 8.4. We're then going to go ahead and add over that 42. So the negative 8.4 plus the 42 is going to give us 33.6. And then we divide by the 42, and that gives us r to be 0.8. So this is always going to work out for us. It's not going to be a situation where you're going to solve out and get an r that's greater than 1 or less than negative 1 in this kind of case here. It's not possible. These problems are designed, and it's going to give us an actual answer that does work. All right. So that's it for our geometric sequences. So the geometric and arithmetic are the only two special types of sequences that we have to truly worry about. Every other sequence that follows some sort of pattern is not really doesn't get its own special name because there's too many of those different possibilities out there. The arithmetic was based on all increasing by the same number, adding, subtracting. Geometric increased by the same number by multiplying or dividing, essentially. Everything else would just be other types of patterns. So we're going to take a look at 11.4, talk about different counting principles. It's going to be a very straightforward concept. It's something you actually talk about hopefully at some point in middle school, but we're just going to review it because its uses in the next two topics, 11.5 and 11.6. So I'll see everyone next time for that.